this video, complex numbers take center stage. The complex numbers are a kind of extension of the real numbers. We often express a complex number z in the form a plus I times b. Here, a is a real number and is called the real part of z. B is also a real number, but it's called the imaginary part of z to distinguish it from the number a. Finally, I, or the imaginary unit as we say, is the solution to I squared is equal to -1. Most complex numbers have, for lack of a better term, partners. We call the partner of a complex number z the conjugate of z and express it either as a minus I times b or as z bar. We can add, subtract, multiply, and even divide two complex numbers, though we'll ignore division for now. We add two complex numbers by simply summing their real and imaginary parts respectively in the standard way. And we subtract one complex number from another by subtracting real and imaginary parts respectively, again in the standard way. Multiplication of one complex number by another is a little more involved, but still it's not difficult. Here, we distribute the multiplication in the standard way and make use of the fact that I squared is equal to -1. Complex numbers help us solve equations for which solutions among the real numbers can't be found. Take for example this quadratic equation, x squared minus 4x plus 5 is equal to 0. Applying the quadratic formula leads us to a situation in which we're confronted with the square root of a negative number. This puzzling situation can be resolved if we factor the negative number under the square root sign like this. Then apply the definition of the imaginary unit I to ultimately express our solutions as a pair of complex numbers. In this case, that pair is the conjugate pair 2 plus I and 2 minus I. With that brief introduction to complex numbers behind us, let's turn our attention back to eigenvalues and eigenvectors, and specifically to finding the eigenvalue-eigenvector pairs for the matrix A shown here. Spoiler alert, these eigenvalues and eigenvectors are going to involve complex numbers. We'll begin our search by finding the eigenvalues of A. Recall, we do this by constructing the matrix A minus lambda times the identity matrix. We then calculate its determinant. We set that determinant equal to 0. Then finally, we solve for the unknown values of lambda. In this case, A minus lambda times I gives us this. Applying our formula for a matrix with 2 rows and 2 columns, we find the determinant to be lambda squared minus 4 lambda plus 5. We set this equal to 0 and solve for lambda. In this case, we've already done the work needed to find a solution. We just solved the same equation a moment ago. Granted, the equation was expressed in terms of x rather than lambda, but that's just a superficial difference. The solutions are still 2 plus I and 2 minus I. To keep ourselves organized going forward, we'll set our first eigenvalue lambda 1 equal to 2 plus I, and our second eigenvalue lambda 2 equal to 2 minus I. Let's now move on to the task of finding the eigenvector associated with lambda 1. We know that the eigenvector satisfies this equation, which we can rewrite in this way. Remember, what we see here is nothing more complicated than two linear equations with two unknowns, v1 and v2. What's more, just like we saw in an earlier video, the solution to this problem is not unique. We have some ability to choose. In this case, we'll choose to set v1 equal to 1. Using the first of the pair of equations on the left, we see that v1 equal 1 implies that v2 is equal to -1 minus I. It follows that the vector whose first entry is 1 and whose second entry is -1 minus I is an eigenvector associated with lambda 1. We found an eigenvector associated with lambda 1, but we still need to do the same for lambda 2. Luckily, there's a shortcut we can exploit. We express v, the eigenvector connected to lambda 1, in this way. Now we can assert that the eigenvector associated with lambda 2, I'll call it u, is the vector conjugate of v. Nice, right? There seems to be a pattern here, as lambda 2 is simply the conjugate of lambda 1. So maybe working with complex numbers isn't so complex after all. Well, that's about it. So let's recap. In this video, we introduced complex numbers, and we saw that some matrices have complex eigenvalue-eigenvector pairs. Once you've mastered the ideas presented in this video, you should be able to determine the eigenvalues and corresponding eigenvectors of any 2x2 matrix. That is, any matrix with 2 columns and 2 rows. You should also be able to handle certain 3x3 matrices too, that is to say, a matrix with 3 columns and 3 rows. This video is just step 1 in your journey toward understanding eigenvalues and eigenvectors, and the role they play in biological modeling. Don't forget to read the course notes, try the assigned problems, and participate in course activities. Maybe even find someone who's never heard of eigenvalues and eigenvectors before and try to explain what it is they are. That's not only a great way to make new friends, it's also a great way to build success in math.